Scene script. Have you ever wondered what binds the universe together? What forms the fabric of existence? In the grand tapestry of the cosmos, the threads that weave together to form our reality are known as space and time. This intricate union is often referred to as spacetime, a concept that serves as the framework within which we perceive our universe. It's a complex idea that has fascinated and puzzled scientists for centuries. Traditionally, spacetime has been understood as a four-dimensional structure. Picture a vast, unending and invisible grid stretching in all directions. Three dimensions account for the physical space around us, up and down, left and right, and forward and backward. The fourth dimension is time, ever-flowing and unidirectional, moving us from the past through the present and into the future. Together, these dimensions create the stage on which the cosmic ballet of the universe unfolds. Now let's take a moment to appreciate the genius of Albert Einstein. His groundbreaking theory of relativity introduced a revolutionary perspective on space-time. No longer was it seen as a rigid, unchanging entity. Instead, Einstein proposed that space-time could be warped and curved by the mass and energy within it. Much like a bowling ball placed on a trampoline, heavy objects like stars and planets cause a dip in space-time, creating what we know as gravity. But Einstein's theory was just the beginning. It opened the door to a universe of possibilities and set the stage for a century of discovery. From the existence of black holes to the expansion of the universe, our understanding of space-time has shaped the way we view the cosmos and our place within it. As we dive deeper, let us explore the current scientific theories about space-time. The fabric of existence is far from being fully unraveled. Each thread we pull reveals new mysteries, new questions, and new opportunities for understanding. So, buckle up as we embark on this cosmic journey through the enigma of space-time. What if space-time is not a rigid framework, but a flexible, malleable tapestry? Imagine a rubber sheet stretched taut. Now place a heavy ball in the middle. The sheet dips, curves around the weight. This is a rather simplistic analogy for how space-time behaves in the face of massive objects. It's a theory that space-time is not fixed and rigid, but flexible. This flexibility allows it to curve and dip in response to the mass and energy within it. The greater the mass, the deeper the curve, the stronger the gravitational pull. This is the cornerstone of Einstein's theory of general relativity. And what of the ripples that travel across our rubber sheet if we were to give our heavy ball a nudge? Well, in the cosmos, these perturbations manifest as gravitational waves. These are ripples in the very fabric of space-time, propagating outwards from their source like ripples in a pond. They're created by cataclysmic events such as the collision of two black holes or the explosion of a massive star. These waves were purely theoretical until the 21st century when, in 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, made the first direct observation of gravitational waves. This was a landmark moment, a confirmation of a century-old prediction, and it opened up an entirely new way of observing the universe. So we have this malleable tapestry, this flexible fabric of space and time, and massive celestial objects that curve and distort it. What happens when this curvature becomes so extreme, so intense that it forms a kind of pit, a point of no return? This, my friends, leads us to the concept of black holes. But that, as they say, is a story for another time. This curvature of space-time around massive objects leads us to the concept of black holes. Imagine a pit so deep, even light cannot escape its grasp. Welcome to the realm of black holes. In the vast expanse of the cosmos, black holes are the most intriguing entities. Their existence is an elegant yet terrifying testament to the power and mystery of the universe. Born from the explosive death of massive stars, these cosmic beasts are places where space-time gets twisted to its limit. When a star much larger than our Sun exhausts its nuclear fuel, it collapses under its own gravity. This implosion creates a supernova, an explosion so powerful that it momentarily outshines an entire galaxy. What remains is a core so dense that it warps the fabric of space-time around it, creating a black hole. These black holes are not merely holes in space, but are intense concentrations of mass, with gravitational fields so strong that nothing, not even light, can escape their pull. They are, in essence, the ultimate space-time abyss. Now, at the heart of a black hole, the laws of physics as we understand them cease to apply. The gravitational pull becomes so intense that it forms a singularity, a point where density becomes infinite. This extreme warping of space-time challenges our understanding of the universe. For many years, black holes were just a mathematical curiosity, a solution to Einstein's equations that seemed too strange to exist. But today, they are at the forefront of our quest to understand the universe. They are laboratories of extreme physics, testing grounds for our theories of space, time and gravity, yet they are paradoxical. Black holes are both simple and complex. They are described by just three properties: mass, spin and charge. But they also harbour the mysteries of singularities and event horizons, pushing our understanding of the universe to its limits. As we venture beyond black holes, we enter the realm of quantum mechanics. Travel to the tiniest scales, and space-time may not be as smooth as you think. Now let's venture into the world of quantum foam, a theory that suggests that the very fabric of the universe might be far bumpier than we could ever imagine. Quantum foam, also known as space-time foam, was a concept proposed by physicist John Wheeler in 1955. He suggested that at the Planck scale, which is the smallest scale that physics can currently describe, space-time is not a continuous sheet, but rather a sea of ever-changing, tiny bubbles. The idea is that these bubbles are constantly forming, collapsing and reforming, creating a frothy quantum foam. But why bubbles, you might ask? Well, these are not your ordinary soap bubbles. They are, in fact, tiny fluctuations in the fabric of space-time, caused by the principles of quantum mechanics. These quantum fluctuations are believed to give rise to particles and antiparticles, popping in and out of existence, contributing to the foam-like structure of space-time. This theory attempts to reconcile two of the greatest scientific theories of the 20th century: quantum mechanics, which describes the universe at the smallest scales, and general relativity, which describes the universe at the largest scales. The problem is, these two theories have traditionally been at odds with each other. Quantum foam is one of the ways scientists have proposed to bridge this divide. Consider this. If space-time is a sea of tiny bubbles, then it's not a smooth ride. It's a bumpy one, full of quantum fluctuations and virtual particles. And these bumps and bubbles could have profound implications for our understanding of the universe, potentially even opening up the possibility of wormholes and other exotic phenomena. This bumpy ride brings us to the concept of wormholes. What if you could take a shortcut through space-time, enter the world of wormholes? Imagine, if you will, a tunnel connecting two distant points in the universe. You dive in at your end and pop out at the other, bypassing the vast cosmic distances in between. This is the essence of a wormhole, a theoretical passage through the fabric of space-time itself. Wormholes are compelling not just for their potential as cosmic shortcuts, but also for the possibilities they present for time travel. This concept, as fascinating as it is, challenges our basic understanding of space-time. After all, we're accustomed to a universe with a strict forward march of time, where cause precedes effect. Theoretical physicists propose that wormholes may allow for travel not just through space, but also through time. You could step into a wormhole and emerge not just elsewhere, but elsewhen. What was once the domain of science fiction could perhaps be reality. But let's pause for a moment and consider the implications. If wormholes exist and allow for time travel, they could create paradoxes. You've probably heard of the grandfather paradox, where a time traveler goes back in time, prevents their grandparents from meeting, and hence erases their own existence. How could such paradoxes be resolved? Some theorists suggest that the universe has a way of avoiding such inconsistencies. Perhaps every trip through a wormhole creates a new parallel universe, where the paradox can play out without affecting the original universe. This leads us to the tantalizing idea of a multiverse, a cosmos filled with an infinite number of universes, including ours. So, wormholes, these theoretical shortcuts through space-time, lead us to question the nature of reality itself. They challenge us to think beyond our three dimensions of space and one of time. They invite us to consider a universe, or rather a multiverse, far more complex and fascinating than we ever imagined. As we navigate these shortcuts, we encounter the idea of multiple dimensions. Are we limited to just 3 dimensions of space and 1 of time? This question has been a topic of intense debate in the scientific community, inducing profound philosophical and theoretical exploration. One of the most intriguing theories that challenge this notion is string theory, a concept that suggests the existence of extra dimensions. In essence, string theory describes the fundamental particles of our universe not as 0-dimensional points, but as 1-dimensional strings of energy. This theory is startlingly beautiful, presenting a symphony of vibrating strings that compose the universe. But here's the crux. For string theory to be mathematically consistent, it requires more than the 4 dimensions we're familiar with. It postulates up to 10 dimensions, with 6 potentially hidden or compactified, as scientists like to call it. These extra dimensions are thought to be extremely small, curled up so tightly that they are beyond our ability to detect. These hidden dimensions could be all around us, woven into the very fabric of space-time, but to remain imperceptible due to their minute size. They are like the tiny fibers in a piece of cloth, too small to see with the naked eye, but integral to the structure of the fabric. What's more, the existence of these extra dimensions could potentially solve some of the most baffling mysteries of space-time. They could provide the missing link between general relativity and quantum mechanics, 2 theories that have been notoriously difficult to reconcile. They might even shed light on the enigmatic dark matter and dark energy that seem to make up the majority of our universe. It's a fascinating idea, isn't it? The thought that we could be immersed in a reality far more complex than our everyday experiences suggest. A reality where dimensions beyond our perception shape the very nature of space and time. Now, having traversed these extra dimensions, let's take a moment to summarize our journey. As we step back to the familiar, we're left with a sense of wonder, a glimpse into the vast and intricate tapestry that is the universe. Our voyage through space-time has been a thrilling one, filled with enigmas and revelations. We embarked on this journey with an exploration of the enigma of space-time, a concept that has baffled scientists and philosophers alike for centuries. We learned that this fabric is not a static entity, but rather a malleable tapestry, constantly shaped and reshaped by the mass and energy within it. Our voyage then took us to the abyss of space-time, the black hole. These mysterious entities are not merely holes in space, but rather they are intense concentrations of mass, bending space-time to such an extent that nothing, not even light, can escape their gravitational pull. They are a testament to the extreme warping capabilities of the space-time fabric. From there, we journeyed into the quantum realm and encountered a phenomenon known as quantum foam. This theory proposes that at the tiniest scales, space-time is not smooth but rather bubbly or foamy, constantly fluctuating and filled with temporary particles and antiparticles. This quantum foam is a testament to the inherent uncertainty and unpredictability of the quantum world. Our exploration of space-time also led us to the intriguing concept of wormholes, bridges or shortcuts through space-time. Though only theoretical at this point, wormholes tantalize us with the possibility of faster-than-light travel and journeys to distant parts of the universe. Finally, we ventured beyond the 4th dimension and pondered the existence of extra dimensions. These dimensions, hidden from our perception, could potentially provide answers to some of the most perplexing questions about our universe. Remember, the fabric of space-time is not just the stage on which the universe unfolds, it is a dynamic player in the cosmic drama itself. This exploration has shown us that space-time is not a passive backdrop against which events occur, but rather an active participant, shaping and being shaped by the unfolding cosmic drama. What does the future hold for our understanding of space-time? As our journey through the fabric of space-time reaches its climax, we now turn our gaze to the uncharted territories that lie ahead. The field of quantum gravity, still in its infancy, is poised to revolutionize our understanding of space-time. This nascent discipline seeks to unify the realms of quantum mechanics, which governs the very small, with general relativity, which governs the very large. It's a bit like trying to blend oil and water, 2 seemingly incompatible theories, into a seamless whole. But if successful, we may finally understand the true nature of space-time. In our quest for unification, researchers are exploring various theories. String theory, for instance, posits that the fundamental constituents of reality are not particles, but rather tiny, vibrating strings of energy. Moreover, it suggests that there might be more dimensions to space-time than we perceive. Imagine that. Then there's loop quantum gravity, another promising avenue. This theory proposes that space-time is not continuous, but is instead made up of discrete, indivisible units, much like pixels on a screen. And just as pixels give rise to the images we see on our devices, these quantum loops could give rise to the fabric of space-time itself. But why does this matter? Well, aside from satisfying our curiosity, a deeper understanding of space-time could have profound implications for technology. Imagine navigating the cosmos using wormholes or harnessing the energy of black holes. The possibilities are as vast as the universe itself. The future of our understanding of space-time is as mysterious and exciting as space-time itself. As we probe deeper into the cosmos, armed with ever more sophisticated tools and theories, we can't help but wonder what marvels we might uncover next. As we continue to unravel the mysteries of the universe, who knows what exciting discoveries await us in the fabric of space-time?